In the previous two lectures on the same topic, we did a few problems apart from theoretical discussions regarding the trajectory that a charged particle would follow in a magnetic field, be it negatively charged or positively charged. In this lecture, we will continue to solve few more questions or problems. We will also discuss a few applications of a charged particle in a magnetic field. So let us come to the first question. In this question, we are to state or identify the laws of physics that are conserved as a charged particle enters a constant magnetic field. We already proved that velocity is retained, velocity magnitude is conserved, which is a combination of components of velocity perpendicular to and parallel to the magnetic field B, that is under root V perpendicular square plus V parallel square is conserved. As the Lorentz force does no work, kinetic energy is conserved, that is half mv square is conserved. Some other things are also conserved. The z component of angular momentum, call it Lz, which is m rho square omega, is conserved. Rho being the radius of circle which charged particle follows upon non-parallel entry into a constant magnetic field, and is given by this expression. Magnetic moment, denoted by mu, is also conserved. We will define magnetic moment in the lecture on multipole expansion. It is given by current into area, the analog being electric dipole moment, which is charge into distance. Now current is charge by time and area is pi rho square. So putting these values and then putting the value of time period and simplifying, we get this value, which is half mv perpendicular square by b. Now the numerator is actually energy involved in plane perpendicular to B, that is transverse to B, and this magnetic moment is conserved. Next, what is Larmor radius? Larmor radius is the radius traced by a charged particle upon non-parallel entry into a magnetic field, and it is given by this expression and is called Larmor radius, Larmor being an Irish physicist. We derived this expression in our earlier lecture. Next question is, how are cyclotron frequency and Larmor frequency connected? Now, what is Larmor frequency? This is to be discussed in a separate lecture series. However, we can introduce it briefly. A particle, say an electron or a proton, has a magnetic moment and hence an angular momentum j. Now, if a direction is imposed upon it, say through an application of a B field, then that j will precess about B with a frequency which is called Larmor frequency, and we can prove that it is half the cyclotron frequency. The precessional motion can be demonstrated as follows. Suppose this is magnetic field direction and this is a vector j, which is the rotational axis of the body. Now at some moment j is here, then it goes there, it comes here, it goes on top and then again returns here. So this type of motion is called precessional motion of the body with respect to the field direction. So this is called precession. It is actually a change in orientation of j with respect to B, and it is a change in one Euler angle, and these things can be discussed separately in a separate lecture series. So Larmor frequency omega L is the frequency of precession of J with respect to the field B, and cyclotron frequency omega is the frequency of rotation of particle in a B field, and cyclotron frequency is double the Larmor frequency. Cyclotron frequency is independent of velocity. Cyclotron frequency depends on charge to mass ratio. So these are the characteristics. Let us do another problem. We have to identify the correct option from the following choices, and the choices are to be read and understood carefully. It says that a charged particle moves into a magnetic field. The options or possibilities stated are: the charged particle can move across the field force free, can move along the field force free, cannot move across the field, cannot move along the field. So here we have to focus on the words along and across. Now along means longitudinal or parallel to B, while across refers to transverse movement or perpendicular movement with respect to B. Now for parallel entry, V cross B is 0 and there is no Lorentz force, so it is a force free situation. So particle can move along, that is parallel to the field, and in a force free situation. So option B is correct, can move along the field force free. Again, for perpendicular entry, Q into V cross B is not 0. There is a Lorentz force which forces charge to move on a circle. The charge bends or curls and charge has to trace a circle. So charge is not force free and also cannot move across the field but has to bend. So option C, cannot move across the field, is correct. So here option B is correct and option C is correct. So in a nutshell, we can refer to this figure. If this is the direction of B and if a particle enters parallel to B, that is along B, it can simply sail across in a no force situation, in a force free condition. But if a particle enters in a perpendicular direction, it cannot move along this direction because this B will bend it. So the particle bends. So this is not possible, but this is possible. Accordingly, option B and option C are correct. Now before going to some more problems, let us discuss a very important aspect regarding utility of studying the problem of charged particle in a magnetic field. There are some problems in physics which are very popular because of their wide application. This problem of charged particle in a magnetic field is one such problem, and every student of physics should learn it thoroughly and have confidence in it. I always feel that it is a good habit of a teacher to repeat things multiple times. So let me once again make a gist of our subject matter of lecture 1C and lecture 1D. So when a charged particle enters a constant magnetic field, its trajectory can be of three types depending upon the manner of entry. If it enters in parallel, then it follows a straight line, as it is under the influence of no force. If it enters the field normally, then the trajectory is circular, while if it enters the field at an angle, that is makes an oblique entry, inclined entry with respect to the field, then it follows a helix, and the sense of traverse of circle or helix will be right-handed for negatively charged particle, while it will be left-handed for positively charged particle. And also, the motion of charged particle in a magnetic field involves conservation of velocity, involves conservation of kinetic energy. Significantly, though velocity magnitude is conserved, velocity direction changes. Let us now mention some very important application with brief explanation. The behavior of charged particle in a magnetic field is used in mass spectrometer, cyclotron, to study Van Allen radiation belt, and also magnetic lens. Let us first come to mass spectrometer. Now, what is mass spectrometer? Or let us first mention what is a spectrometer. Spectrometer is an instrument that is used to separate various components, or we can put it in this way, that it is generally used to split and measure various wavelengths. Now, in this case, we are talking about mass spectrometer. So, this instrument will separate charged particles depending upon their mass, based upon their mass. And this is the principle used, or rather, this is the working formula. Rho is proportional to m, m being the mass of the charged particle. Now, this is a schematic diagram of mass spectrometer. This is the positive ion source. In our discussion, let us take for convenience positive ion source. The ions are coming out from it. They are accelerated through a potential difference V. So, they gain an energy of half mv square, which is equal to q into V as they rush through this potential difference. The particle now pass through the velocity selector, where magnetic field B is applied in the upward direction, say, and an electric field is applied in this direction from plus to minus. Now, as this charged particle enters in this region, it experiences a Lorentz force. Now, in what direction? The positive particle enters into this velocity selector and it sees a magnetic induction upward and experiences a Lorentz force in this direction, that is towards positive plate. So, E is from plus to minus, but the Lorentz force is from minus to plus, that is Lorentz force opposes the field. So, the magnetic force and the Coulomb force, they are oppositely directed. So, clearly we will have three types of particles depending upon their velocity. The first type of particles are those for which Q into E Coulomb force is equal to the Lorentz force QVB, so that Q cancels out and we have V equal to E by B. So, these particles move straight as on their path electric or Coulomb force and Lorentz force balances. So, there is no net force and they move straight out. It is these particles which are selected by the velocity selector. For Q greater than QVB, the Coulomb force dominates and particles are deflected towards negative plate. So, they are removed from the beam and they have V greater than E by B. Now, mind it, we are speaking of positive ions and not electromagnetic radiation, and so V greater than E by B is possible. Again, if QE is less than QVB, then the Lorentz force dominates and particles will be deflected towards the positive plate and therefore are removed from the beam, as they have V less than E by B. The filtered or selected positive ions having V equal to E by B now enters into this chamber where B acts up. Again, positive charged particles are acted upon by a Lorentz force which bends them and they trace this circular path. So the positive ions enter into the chamber, sees a B field up and experiences a Lorentz force that pushes them in this direction, and therefore they trace these circular arcs. So particles of larger mass will trace a bigger circle, that is circles of larger radius, while particles of lower mass will trace circles of smaller radius. So the points of strike are different and therefore they are separated. They deposit at different places. Here light particles, here heavier particles. So in this way the mass spectrometer separates charged particles. Next application is cyclotron motion, which is a particle accelerator that was developed by Lorentz in 1930. It is a device where charged particles can be accelerated through suitable use of and tuning of electric field and magnetic field. Particles follow spiral tracks. We will discuss it in a different lecture series in particle physics under some lecture number starting with P. Also there we will be solving some problems involving cyclotron. The next application is explanation of Van Allen radiation belt. Here we will come across terms like magnetic bottle or magnetic mirror. Now what is Van Allen radiation belt? Now this is Earth and this is the rotation axis of Earth and this is the magnetic axis of Earth. Now Earth has a magnetic field which is called geomagnetic field. It is the magnetic field extending from Earth's interior onto space. It interacts with stream of charged particles that are emitted by sun and which is also called solar wind. Earth has a north pole and a south pole. Now if we move up from Earth's surface, one finds one layer between 0.2 to 2 times Earth's radius, and this layer contains trapped charged particles. This is called the inner Van Allen belt. Again, if one moves up further to say 3 times to 10 times the radius of the Earth, then again one finds trapped charged particles, and this is called outer Van Allen belt. Particles from solar wind are captured and held around. And how is this trapping possible? The trapping can be explained if we study the behavior of charged particles in a magnetic field, and also if we take care of the radius described by charged particle moving in helix in a magnetic field when it enters obliquely. And very importantly, the radius is inversely proportional to the magnetic field. Now let us explain these things. Now consider a region where there is a magnetic field. Now these are two regions which are called neck. It is such that the intermediate region has a constant B, and let us call it B0, and beyond this neck B is larger on this side as well as on this end, and maybe it becomes gradually larger. Now how is it evident that the field here is large? It is evident if we look at the field lines carefully. In this region, field lines are widely spaced and number of lines per unit area is small, so B is weak here. But in this region, lines are crowded. We have more number of lines per unit area in this region. So B is large here as well as in this end. Now this type of region can be easily constructed by considering a long solenoid. We shall define and discuss about solenoids after we do Ampere's circuitous law, but we can talk about it briefly. Solenoid is a device like a coil of wire which creates a magnetic field from current, and the magnetic field can be used to create linear motion. So a solenoid converts electrical energy to mechanical energy. Now consider a cylindrical region upon which wires are wound. Now winding, or the number of turns per unit length, is dense at the ends, and so this gives a strong B at the ends. But in the intermediate region, number of windings per unit length is small, and this gives a weak B. We can compare such arrangement with the earth or the geomagnet. The magnetism is most prominent at the poles, the North Pole and the South Pole, and these are large B regions, while regions other than the poles are low B regions. Now, having described such structure, let us now investigate how a charged particle would behave when it gets into such a region. Say, particles coming from solar wind or having a cosmic origin gets into or enters somehow in this region. Let us consider a particle that somehow made way to the weak magnetic field region and entering into this B region at an angle, that is making an oblique entry. It will trace a helix, and this helical motion was derived and discussed at length in previous lectures. Now in this low B region, the radius of helix is large, because if B is small then rho is large. Now on moving along the helix, it ultimately comes to the strong B region. Strong B implies smaller radius, so here rho will be small. Now all this it does to keep magnetic flux constant, and magnetic flux is integration B dot ds, that is field into area. Here field is low, so area of cross section large, and in this region field is high, so area of cross section is low. Now if you ask that why magnetic flux is required to be constant, etc., you have to refer to what we call magnetic circuit, that might be discussed in a separate lecture series, say on magnetic materials. We are not interested about those right now here. Again, we discussed in the first problem that magnetic moment is conserved and is given by this expression. Clearly, for B large, to keep mu constant, V perpendicular is needed to be large, and since energy is constant, if V perpendicular is large, this automatically means V parallel will be small, and ultimately for some B, V parallel will be 0. So this means when a charged particle enters into a strong B region, its V parallel, that is the longitudinal velocity, will be 0, and this means the forward movement ceases, forward movement stops, and the particle will reflect back. So the charged particle now starts to move back in helical path again from strong field to weak field. So the journey is like from low B to strong B, and then from strong B to low B. In other words, as it moves from low B to a strong B, it suffers a reflection at high B or strong B, and then it retraces its path. That is why the strong B region is called magnetic mirror, and the particle now feels as if trapped in this region, and this region therefore behaves as a magnetic bottle. It is trapped magnetically at both ends, and the charged particle cannot escape during its transverse movement because Lorentz force has an eye on it, and always the Lorentz force compels it to move on following a helix, so it has no sideways escape. In truth, it has no escape at all. It is trapped in the Van Allen radiation belts, and there are interesting effects of it that can be discussed separately elsewhere. We come to another important and interesting application of charged particle in a magnetic field, and that is called magnetic lens. In optical case, lenses focus light at a particular point, and the phenomena involved is refraction. In electron microscopy, one uses instead an electromagnetic lens or magnetic lens, and focus is achieved through Lorentz force. Now these are copper coils or wires enclosed within soft iron pole pieces. When current flows in coils, magnetic field is produced. Now the magnetic field that is produced by the coil and the pole pieces has the following characteristics. It is rotationally symmetric, and most importantly it is inhomogeneous. Now, inhomogeneity is because the B field is weak at the center and strong close to the bore of the pole pieces. So here it is strong and weak at the center. Now what is the effect of this inhomogeneous field? The electron beam from source enters into this magnetic field and suffer helical motion. Electron close to the axis, that is at the center, are in weak field and they are less deflected, while electrons passing further from the axis, that is near to the bore of pole pieces, are more deflected. So these are slightly deflected while these are deflected by great amount. So the overall effect is focusing of electron beam to a spot. The image is rotated due to helical path, and we are not going to discuss details. We now come to the remaining set of problems. Let us take up this problem. It speaks of a positron that is entering into a magnetic field at an angle 30 degrees. So it is an oblique entry, and we have to find the nature of trajectory where the initial velocity has been given. Now oblique entry means it is a helix and its positron positively charged, which means the helix will be left-handed. So if B is along this direction, then the left-handed helix will be of this type. Let us calculate the transverse velocity, which is v sine theta. We can put the values and end up with 10 to the power 3 meter per second. The longitudinal velocity is v cos theta, which similarly we get to be of this value. And now it is easy to find out the frequency if we use this expression omega equal to qb by m, put the values, and you can check the results. The radius of the helix is v perpendicular by omega, which turns out to be of this value, and the time period of rotation is here. The frequency, linear frequency, is this one, and pitch is given by v parallel into t, or the longitudinal velocity times the time period, which turns out to be of this value. The next problem is of similar type, where a proton has entered into a magnetic field, and the condition given in this question is that the helical path is such that the radius of the helix and the pitch are equal. So we equate the pitch to the radius. The expression of pitch is v cos theta into time period, and the radius is v sin theta by omega, and if we equate them we end up with tan theta as omega t, and omega t is 2 pi, so theta is just tan inverse of 2 pi, which turns out to be 81 degrees. The next problem is MCQ type. We have 4 options, and the problem is that an electron has been spoken of, and this electron of mass m moves into a magnetic field, and the field direction is along I cap, while the velocity with which it enters the field is v1 I cap plus v2 j cap. Now we have to find the correct option, and the options predict about the trajectory, radius and pitch. Here electron is involved, which has negative charge. Electron enters into the field which is along I cap with this velocity, which has components along I cap as well as perpendicular to it, and this means it's an oblique entry, so the charge will trace a right-handed helix. So out of all these options, A and C, which involve right-handed helix, are chosen. Now next we have to find the radius. The radius is mv perpendicular by EB or QB. Here v perpendicular is actually perpendicular direction to I cap. So perpendicular direction to I cap is j cap, and the component is v2. So we will have v2 here. And again, A we have mv2 by EB, and in C also we have mv2 by EB. So we cannot decide which is correct, and therefore we have to go to the pitch. Now the pitch is V parallel into T. You have to identify the parallel component. Now B is along I cap, and this component is along I cap. So this is parallel to B, and therefore pitch is V1 into 2 pi m EB, and we find that C has 2 pi m V1 by EB. So C is the correct option. This is a similar problem, but an extension of the earlier one, because now we have charged particle entering into the field which is along k cap, and the velocity of entry is 4 I cap plus 3 j cap, which means velocity is in the xy plane and the field is along k cap. So the entry is perpendicular to the field, and therefore the motion will occur in a circle. So helix will not be traced. V dot B, we can find it, V dot B turns out to be 0. So motion is in xy plane, particle traces a circle, and the pitch will be 0 because no helix is traced. So out of the 4 options, options containing helix are not possible. So C and D, out of C and D we have to make the right choice. Now let us find the radius. The radius is mv by qb. Now here v is the velocity in the xy plane, and the magnitude of velocity in the xy plane is 5, and therefore rho is 5m by 8q, and the time period is 2 pi m by qb. B is 8, so it turns out to be of this value. So we can just have a check. So D is the correct answer because D contains this rho, D contains this T. We take up the next problem. Here an electron is emitted from an electron gun, and then it is accelerated to a potential difference of this amount, 2 kilovolt, and then it enters a B field, and we have to find the trajectory of the electron, and the manner of entry is also stated here. The manner of entry will be the initial velocity is perpendicular to the field, or the initial velocity makes an angle 30 degree to the field. Now since electron is coming from electron gun, we have to first find the energy with which it enters the magnetic field. So the energy gain of the electron will be half mv square, which is equal to EV, V being the potential difference through which the electron was sent. And from here we get the velocity, and putting the values of mod E, then V is 2 kilovolt, and the mass of the electron, we end up with this value of velocity. So this is the initial velocity of the electron. Now in question A, the particle makes transverse entry, and transverse entry means V is perpendicular to B, so the trajectory is circular, and since it is an electron, it will be a right-handed circle, and the radius is as per the formula mv by qb, and if we put the values and simplify, we end up with rho as 1 millimeter. The frequencies are of these values and the time period is this one. Now if this particle were a positive charge, it would have entered the region in this manner and felt of B downwards, and then it would experience a Lorentz force in this direction, so that it would have bent in this way. But since it is an electron, it will not bend in this way, but will rather bend in this way. So this is the circle, the right-handed circle that is traced. Regarding the next question of oblique entry, the trajectory will be helix, and obviously again a right-handed helix. So B is down, so it will be a right-handed helix, and V perpendicular is V sine theta, theta is 30 degrees, and V parallel is V cos theta, so we have this value. So the radius of the helix will be half of the earlier value, that is, it is 0.5 millimeter. Have a check at the calculation. And the pitch will be V parallel into T, so V cos theta into time period, and if we put the values correctly, we end up with 5.47 millimeter. And it follows that the values of frequency and time period are velocity independent. In this problem, a chamber is considered where there is a B field and an electron enters in this field with this velocity normal to the field. We have to find the nature of the path and dependence of the path on velocity. Now this is an easy problem. Velocity is perpendicular to B means we have a circular track, and it is a right-handed motion because electron is involved, and the radius being of this value if things are put correctly, and the time period and frequency are velocity independent. Now comes another MCQ, that is multiple choice question, which says that a magnetic field B varies from point to point in magnitude but has a constant direction in a region, and a charged particle enters into this region and it travels undeflected along straight path, and we have to find the angle of initial velocity and the field. Now we did earlier that traveling undeflected means entry of charged particle in the magnetic field in parallel or in antiparallel. For parallel entry it is theta equal to 0, and for antiparallel entry it is 180 degrees. So the option C is to be clicked. This is a similar type of problem which says that charged particle enters a strong non-uniform field that varies both in magnitude and direction, and the particle emerges from the chamber with a complicated trajectory. Now what would be the final speed and the initial speed? Now we have earlier seen that in case of charged particle in a magnetic field, velocity is conserved. Now if velocity is conserved, that means the initial speed and final speed have to be same, and therefore A should be the correct option. Now in this problem, an electron enters a chamber where an electric field is there, and the electric field is along I cap, and the direction of entry of the particle is j cap. Now a magnetic field is to be applied in this chamber such that the particle will emerge out along j cap. So entry is along j cap and exit is also along j cap. So the particle should travel undeflected. But in this region there is a electric field which will exert force on the charged particle, which is electron. So let us come to this diagram. So this is electron, negatively charged particle, enters with velocity v, and j cap is the direction of entry, and this is the electric field. So the Coulomb force on electron will be minus E I cap, that is along this direction. Now this force should be cancelled by a magnetic Lorentz force along this direction, so that net force will be 0 and the particle will exit along j cap. Now Lorentz force along this direction is needed, so we write this is the Lorentz force, which is equal to Q into V cross B. Now Q is minus mod E and value of V is given to be V into J hat, and the value of B is not known. So the problem is actually minus J cap cross what gives us I hat, and this should therefore be minus K cap. We can check it easily. This part cross this, if we put minus B into K hat, it gives us Lorentz force along I cap. So the magnetic field will be along minus I cap. So the answer is B. And this Lorentz force cancels the Coulomb force, so that particle will emerge undeflected. We come to the last problem of this lecture. The thermal speed of a proton in the solar wind is given, the magnetic field is given, and we have to find the Larmor radius. The Larmor radius is of this value, which we told earlier, and if we put the values correctly, we end up with this expression. So the radius is of a huge value, 104 kilometer. Let me end this lecture with this quote. I am quite surprised that it happened during my lifetime. It is nice to be right about something sometimes. Now this was a quote from Peter Higgs when Higgs boson was detected. Success has no shortcut. Even if we succeed through a shortcut or through a back door, we will be exposed sooner or later. Thank you.